Hello, I am Shushmit Dhar and I'm going to present our paper, Spray Icing on ONEGA Vessel, a comparison of liquid water content expressions. This work is done under the Norwegian Research Council project's prize. Please visit our website for further information regarding our project. Commercial fishing is rated as one of the most dangerous occupations. With increased seafood demand and trade leading to substantial monetary gains, fishing vessels are often tempted to operate in severe weather conditions. In 2019, 671 vessels were operating in the Arctic Polar Code area, making 45% of the total ships there, sailing an aggregate of 4.82 nautical miles. One such significant hazard that the fishing vessel encounter while operating in cold region arises from ice accretion. The past observation on ships indicate sea spray as the main contributor towards vessel icing. Icing not only poses a safety hazard for crew working on the vessel, it may also damage communication and safety equipment or other critical and essential machinery. The maneuverability of the vessel can be reduced, but more threatening is that icing can eventually destabilize and capsize the vessel. When a vessel accumulates ice on the top side, the center of gravity is shifted upwards, consequently reducing the metacentric height. Thus, the righting lever, which determines the restoring moment to bring back the vessel to its initial state when healed, is gradually reduced, and therefore the vessel loses its capability to upright. The smaller vessels have lesser residual stability compared to larger vessels, and thus lower amount of ice accretion can destabilize and make them more prone to capsizing due to sea spray icing. A catastrophic ship icing incident in the Arctic water was the sinking of fishing vessel ONEGA, which led to the loss of 17 lives on 28 December 2020 while fishing west of Yuzhny Island in the Novaya Zemlya archipelago. There were 19 crew members on board, out of which only 2 were rescued, 1 found dead, and 16 were not found. According to the Ministry of Transport of the Russian Federation report, the vessel apparently encountered heavy ice accumulation, which reduced the initial vessel stability. The investigation mentioned about the unjustified risk admitted by the captain and the crew of the vessel when deciding on line hauling in difficult hydrometeorological conditions. The stormy weather and the presence of an open hatch for retrieving fish using a fishing tackle led to the increase of seawater into the premises of the vessel located on the main deck. This water ingress added to the initial negative stability and a sharp increase in heel, leading to the sinking of the vessel. This paper focuses on estimating the amount of ice accumulation that presumably destabilized the ONEGA vessel, which ultimately led to its capsizing. Firstly, the minimum ice accretion thickness that decreased the initial stability is estimated by modeling the vessel using a hull modeling program and carrying out stability calculation. Then another method is used to compare this estimate utilizing the Marine-Icing model for the Norwegian Coast Guard MINCOG. The model is adjusted to estimate the total ice accumulation throughout the voyage for ONEGA until it capsized. Next, checking the dependency of the MINCOG method output on different empirical formulations of liquid water content and spray frequency proposed by researchers for computing the spray flux. Finally, identifying the parameters to consider in order to make the icing model more robust. In order to carry out hydrostatic computations, a 3D model was recreated using ship according to the lines plan, general arrangement plan, tonnage calculations. All the exposed parts and projected lateral areas of the vessel where icing can take place are identified. It is assumed that the vessel was at least maintaining the minimum stability criteria prior to accretion of metacentric height 0.35 meters plus the icing allowance. The last updated draft of the vessel by ship crew was 4 meter on its AIS. Accordingly, these values are applied in the hydrostatic computations. Adding ice loads on the exposed parts, the minimum thickness of ice accretion on the ship, which reduces its metacentric height to 0, is evaluated. Next, the MINCOG model is modified to evaluate the ice accretion on ONEGA. This model is chosen as it is verified against icing data from ship types in the Arctic waters. The model has delivered higher verification scores than previously developed ship icing models and nomograms, and it is also the present operational model for providing sea spray icing forecast at the Norwegian Meteorological Institute. The MINCOG output gives an instantaneous icing rate as a warning and is not input for integrating total amount of icing over time. In the study, according to the MINCOG model, the vessel ONEGA experienced icing over a span of nearly 212 hours. Hence, the ice accumulation has to be evaluated over this period to be able to compare it with the amount calculated from a stability model. In order to do so, initially the spray-flux calculation is altered and calculated without the time averaging term. Then, to compute the ice accretion for only during each spray event, this value is multiplied with the spray duration and the spray frequency for the vessel voyage speed for that hour taken from the AIS data. The computed ice thickness is integrated for every hour for the period the vessel was accreting ice. It is assumed that the vessel started accumulating ice from 19 December 2020 0900 UTC until the vessel was lost and is not accounted for any melting or de-icing. It is considered a fair assumption as the air temperature dropped to negative at this time and always remained below -3 degrees Celsius during rest of the period. And according to a survivor, the whole ship was covered with ice. When the vessel began accreting ice until it capsized, yielded an ice thickness estimate of 19.4 centimeter by this method. One of the key parameters that the output of the MINCOG model is dependent on is the spray flux, which in turn consists of important terms such as the liquid water content and the spray frequency. For this term, several empirical formulas have been proposed by different researchers. For the spray frequency, mainly two formulas are used. The first one for bigger ships, assuming every fourth wave ship collision creates one spray jet. Another for medium-sized vessels like ONEGA, it is assumed that a spray jet occurs for every second ship wave collision. The figures are presented to show the variation in the ice accumulation in the ONEGA case utilizing the MINCOG model if different formulas are used for these two parameters. It can be seen from the graphs in a longer time period the spray frequency plays more important role. Comparing the results from the two different methods, it is noticed that the MINCOG method yields to some extent lesser ice accretion thickness than that from the stability calculation. For the ONEGA case, one plausible reason for lower estimation in the amount of ice accumulation by the MINCOG model method is that the model does not account for wind-generated spray and atmospheric icing. The model is built on the spray generated from only wave-ship interaction as it is believed to be the most dominating spray flux source. Some researchers have argued that the wind-generated spray would not affect icing on and above the deck of a vessel. However, their conclusion is based on limited observations. Nevertheless, at the location where ONEGA was fishing, the contribution of wind-generated spray towards vessel icing should not be ignored. This location is in close proximity to mountains, which is associated with complex wind flows such as gap winds, trap levees, and downslope windstorms, which may cause wind speed to exceed 30 meters per second. Also, the temperature at the lee side of the mountains may be extremely low despite adiabatic warming when descending the lee slope due to low initial temperature upstream of the mountains in these areas in wintertime. Also, the downslope windstorm is associated with the hydraulic jump and type 2 rotors with rising motion, which can generate significant wind generated sea spray and lift larger droplets to higher elevation, which may contribute to vessel icing. Vessel icing events during such a phenomena has been reported in coastlines of northern Norway and Svalbard and in the Russian coast of the Black Sea. Sheshkatova's investigation found a possibility of frequent hazardous vessel icing event during a downslope windstorm phenomena on the west coast of Novaya Zemlya, which is regularly observed here, around 138 days per year. The study also found that the ONEGA incident happened during a downslope windstorm, leading to wind gusts up to 32 meters per second. The study aimed to provide a comparative overview of the amount of icing the vessel accretes during its voyage compared to the amount calculated by an operation weather forecasting model (MINCOG). The MINCOG method yields to some extent lesser ice accretion thickness than that from the stability calculation. One probable reason is that, like some other ship icing model, the MINCOG model spray flux expression does not include the contribution of wind generated spray. Also, the empirical formulas are based on limited observations. There is a need for more spray measurement data to develop a more appropriate spray flux formulation in order to estimate ice accumulation over a longer duration and make icing model more robust.